Hello and welcome in. We are in our Chapter 2 material, thinking about coordination chemistry, the properties of metals, and how they behave as parts of compounds. Previously, we talked about our transition metal properties, and then in our previous video, we introduced this idea of coordination chemistry. But now we want to look into a theory of how these coordination compounds behave, and a little bit of why they behave that way. This will be our crystal field theory, a nice accessible theory explaining some of these transition metal properties. All right, so our crystal field theory is going to be able to explain these properties. The properties that we're going to look at, well, we can think about magnetism. How many unpaired electrons are in these compounds? Well, maybe it's not exactly what we'd expect based on our transition metals. Turns out when we form these complexes, we get different magnetic properties. We can also look at our spectroscopic properties, color and absorption. We end up with a variety of interesting colors for these transition metal compounds due to their, well, electrons jumping from one orbital to another orbital. Crystal field theory can give us some intuition about why they behave this way. And so there we go. Let's jump into it. Here are our ideas for crystal field theory. We want to be thinking about our metal surrounded by ligands. Well, our metal is this positively charged cation, which acts as our Lewis acid. Our ligands are these compounds or ions that contain lone pairs of electrons. Those lone pairs act as a Lewis base and attach themselves to the metal. Well, on our metal just by itself, there are d-orbitals. Those are the highest energy filled orbitals for our metal, the d-orbitals. On our ligand, we have a lone pair of electrons coming in to bond to that metal. The electrons on our metal and the electrons on our ligand are going to repel each other. Right? Opposite charges attract, like charges repel. If we have two groups of electrons coming in contact, they are going to be unhappy. There is this repulsion effect when we have a strong overlap between our d orbitals on the metal and our incoming ligands with their lone pairs. We can try to look at the specific overlaps between, well, the individual d orbitals and the incoming, what we call crystal field, the incoming field of ligands. Let's start with octahedral complexes. For our octahedral complex, we have 6 ligands. Each of them is 90 degrees apart. These 6 ligands will come in and bump into our d orbitals. Let's remind ourselves what these d orbitals look like. There are 5 of them. 3 of them on the right are in between our axes, in between the y and the z axis, in between the x and the z axis, in between the x and the y axis. We have 2 other d orbitals, one of which is exactly on top of the x and y axis. The other of which is directly on top of the z axis with, okay, I like to call this a little donut, which is on the xy plane. If we're imagining our ligands coming in, bumping into this metal, these ligands are going to bump into our dx squared minus y squared orbital very strongly. There's going to be a lot of overlap and a lot of repulsion with this d orbital, which is exactly on those axes, exactly where these 4 ligands are trying to bond. This orbital is going to be elevated to a much higher energy level because of that repulsion. Same thing for the dz squared orbital. We have a lot of electron density on the z axis, and we have 2 ligands that are also trying to come in on that z axis. We also have this donut with a little bit of electron density on the xy plane, well, we also have 4 ligands coming in on that xy plane, also causing some repulsion. These 2 orbitals have a lot of repulsion with those incoming ligands. They'll be raised to a much higher energy level. The other 3 orbitals are in between the axes. They are going to dodge our ligands a little bit, but not completely. There's going to still be some repulsion between our ligands and these other 3 d orbitals. Not as much repulsion, but there is going to be some repulsion for these 3 orbitals. Here is our result. Okay, we have an energy diagram. We're starting with our 5 d orbitals. This is our metal before any ligands come in. Once those ligands come in, 2 of our orbitals get bumped into, well, head on. We have a lot of repulsion with the z squared d orbital and the x squared minus y squared d orbital. These get raised to a higher energy level. They started down here, and they are raised up to a much higher energy level because of that repulsion. Our other 3 orbitals are also raised to a higher energy level, but not as high because there is less repulsion, because there's less overlap. The result here, we have our 5d orbitals in our complex, which are no longer degenerate, which are no longer the same energy level. And there is a gap. There is an energy difference between 3 of our d orbitals and the other 2. We call this gap delta, or we call this our crystal field splitting energy, CFSE. This crystal field splitting energy can either be large or small, and it will dictate these spectroscopic and magnetic properties of our compound. Let's look at this. When our delta is large, if there is a large splitting energy, if there's a large gap between our d orbitals in this compound, we call this a strong field compound, or perhaps we call this a low spin compound. Our electrons will follow the Aufbau principle as we expect. Electrons in our d orbitals will fill in down low, pair up down low, and then finally fill in up high. Imagine we have something like iron 2 plus. Iron 2 plus has the configuration 3d6. In our metal by itself, we have those 6d electrons. In our metal as part of a complex, it will also have those 6 electrons. We need to fill our electrons in over here, just like we did before. If we have a large delta, a large crystal field splitting energy, those electrons will have to pair up down low before going up high. We call this low spin because we tend to have more paired electrons. We call this strong field because there is a lot of repulsion from our ligands, and that crystal field splitting energy is larger. This delta tends to be large when we have certain ligands. Cyanide, nitrogen monoxide, carbon monoxide. These are some quote unquote strong field ligands. Alternatively, sometimes we can have a delta that is small in our octahedral complexes. Our small delta is called weak field, or perhaps high spin. In this case, we are going to not follow the Aufbau principle and instead spread out up into those higher energy orbitals before having to pair up down low. The reason here is because that delta is small. The price in terms of energy of putting an electron up high is going to be smaller than the price of putting 2 electrons into that same orbital, right? The repulsion from pairing electrons up. In our iron example, we can still have 3d6 as our electron configuration, but if we have a weak field ligand, we can fill in our 6 electrons, well, same starting thing, fill them in down low first. But once we have our low energies partially filled, well, we can spread out first before having to pair up down low. 1, 2, 3, 4, 5, 6 of our d electrons. If that delta is small enough, we'll spread out into those higher energy orbitals before having to pair up. This situation arises when we have ligands like water, hydroxide, some of these halogens. These ligands will have maybe less repulsion with our d orbitals, leading to a smaller delta, a smaller gap in between the orbitals, and the ability for those electrons to spread out first. We gave some examples for ligands that tend to be strong field or weak field. Well, we can actually list all of our ligands in order of exactly how strong or how weak they tend to be. This is known as the Spectrochemical Series. On the left side, we have our weakest field ligands. On the right side, we have our strongest field ligands. We can have a cutoff point. After water, our compounds tend to be strong field, with those electrons pairing up down low before spreading out. Everything before water, and including water, tends to be weak field, tends to have our electrons spread out up high and then pair up down low. With this intuition, we can start to look at some of the properties of our complexes. Well, light is absorbed when electrons move from one orbital to another orbital, just like we've seen in previous chemistry courses. Well, this relative energy between our lower energy d orbitals and higher energy d orbitals, right? This delta, this crystal field splitting energy, dictates what energy of light is absorbed by our complexes. As it turns out, this delta oftentimes corresponds to visible light. It does depend on the specific metal and ligand that we have in our complex, but it is oftentimes in the visible light region. What that means is our complex will also appear one of the colors that we can see with our eyes. We can do some calculations, right? The energy of light that is absorbed is related to its frequency based on the equation with Planck's constant. And the wavelength of our light and its frequency are also related based on c, the speed of light. If you want to know what color your compound will absorb, well, that's related to its frequency, that's related to its energy. This gap in energy directly corresponds to the color of light that is absorbed. If we have a large splitting energy, we'll absorb light with higher energy. If we have a smaller splitting energy, we'll absorb light with lower energy. There's a wrinkle here. As it turns out, if you have these complexes, what light gets absorbed is actually the complementary color to what color it appears. If we are absorbing the red colors of the visible light spectrum, that does not mean our compound is red. That means our compound is the complementary color of red. We can have our artist color wheel: red, orange, yellow, green, blue, purple. If you are absorbing one of these colors, you want to go through the middle to the exact opposite side of the color wheel. That is the color you will appear. If your compound absorbs red, it will appear green. If your compound absorbs orange, it will appear blue. If your compound absorbs yellow, it will appear purple, so on and so forth. Right? So one extra hoop to jump through in order to figure out, well, why does our compound appear to be this color? Well, it appears that way because that's the color that is passing through. that is the color that is not absorbed. The color that is absorbed is the complementary color, which, okay, then we can start to do our calculations using our light equations. We have a practice question. Can we rank these compounds from the lowest splitting energy to the highest splitting energy? And okay, we have a few ways of doing this. We can look at our chemical formula, examine the ligands that are attached, and use our spectrochemical series. We can also look at the color that this appears, figure out what color is being absorbed, and then rank the splitting energy based on the energies of those colors that are absorbed. We can just compare two of these real fast. If we have our first compound, cobalt with 6 ammonias attached, hexaamine cobalt 3. Ammonia is a strong field ligand. This will absorb light with high energy. This will have a large delta. Comparing this to, okay, we have 5 ammonias and 1 chlorine. Chlorine that we've replaced one of our ammonias with is going to be a weaker field ligand. If you replace a strong field ligand with a weak field ligand, the overall field will become weaker. We expect the splitting energy for this second compound to be smaller than the splitting energy for our first compound, based on the ligands. We can also think about this in terms of our colors. Our first compound absorbs the complement of orange yellow. Well, if it appears orange yellow, that means it is absorbing in the blue or purple range. Our second compound, it appears to be purple, which means it is absorbing in that yellow range. If we are absorbing blue light, that is high energy, compared to absorbing yellow light is lower energy. All right, 2 different ways to get to that same answer. Our hexaamine cobalt 3, that first complex, this will have a large delta. Our second complex, pentaamine chloro cobalt 3, this is going to have a smaller delta. Feel free to try this out with the other 2 complexes on this slide. Good practice to have. We have another practice problem. Feel free to pause here and see if we can get the answer. For us, we'll move on. Happy to go through this with you at some point if you'd like. All right. One of the other properties we wanted to examine for these complexes is the magnetic properties. Well, our complexes can either be paramagnetic or diamagnetic. Paramagnetic corresponding to electrons that are unpaired in our complex. Diamagnetic referring to compounds that have every single electron paired with another inside of our complex. Well, we can look at our electron configurations to determine if something is paramagnetic or diamagnetic. There's the caveat, however. The size of our delta will correspond to how we fill our electrons into that electron diagram. When we have a large delta, we tend to pair our electrons down low. Right? When we have strong field ligands, we have low spin complexes. Our electrons are paired up down low before spreading out up high. On the other hand, when we have high spin complexes, this is when our delta is small. This is when we have weak field ligands. Our electrons can spread out first and have, well, even more unpaired electrons than some of our other compounds. We have some practice problems. Can we draw the energy diagram for a high spin octahedral complex with a d7 electron configuration? Is this paramagnetic? Is this diamagnetic? Let's pause and see if we can get it. All right. If we're thinking about our energy level diagram, we have an octahedral complex, which means we have 2 orbitals that are high energy and 3 orbitals that are lower energy. we have d7 as our electron configuration. We can have 1, 2, 3 electrons always fill in first, down low. Then we need to consider, okay, strong field, weak field, high spin or low spin. High spin corresponds to weak field, which means our electrons will spread out first and then pair up if they have to. There are those 7d electrons filling into that energy diagram for our octahedral complex. This is going to be paramagnetic because we do have 3 unpaired electrons. A follow-up question, what if we have a low spin complex? We'll leave this one as practice, but see if the answer is the same, see if the answer is different. All right, we've been spending a lot of time with our octahedral complexes. Well, there are 2 other common geometries that we want to consider. We can also have tetrahedral geometries. We can also have square planar geometries. The same postulates apply, the same rules apply, but now the overlap is going to be a little bit different. In our tetrahedral complex, we need to consider the metal and its d orbitals and how our ligands will come in and disrupt those orbitals. Here is that tetrahedral field. Our ligands are coming in between the x and the y and the z axes. They're going to bump into our d orbitals to some degree, but not to an equal degree based on where those d orbitals are. As it turns out, we have the opposite situation as we did for octahedral complexes. Our orbitals that are on top of the x and the y and the z axes have less overlap than our orbitals that are in between the x and the y and the z axes. Therefore, we have 2 orbitals that are repelled just a little bit, and we have 3 orbitals that are repelled more. This is our result. Our metal by itself has those 5d orbitals. Once those ligands come in, 3 orbitals get raised to a higher energy level. 2 orbitals get raised to, well, just a slightly higher energy level. Again, we can call this our delta, our crystal field splitting energy, and we want to remember this pattern. For octahedral complexes, we could have high spin or low spin, right? Strong field or weak field situations, depending on the ligand. Well, for tetrahedral complexes, the answer is simpler. With only 4 ligands coming in, there's much less repulsion in general, and so our delta is always small. We are going to have high spin electron configurations 100% of the time for our tetrahedral complexes. Lastly, we can consider our square planar complexes. These complexes have 4 ligands coming in instead of 6 in our octahedral complex. We're missing the ligand coming in on top from the z-axis and on the bottom from the z-axis. So we could do some calculations. Where is the strongest overlap between the d orbitals on our metal and these 4 incoming ligands? As it turns out, we have, well, 2 orbitals that miss those ligands almost entirely. We have 1 orbital that only gets hit on its little donut part of its orbital. We have 1 orbital that has a fair amount of repulsion in between all those 4 ligands. And we have our final orbital that gets hit by those incoming ligands almost directly on all 4 parts of the orbital. The pattern that results is, well, 2 orbitals that are only slightly elevated in energy, and then 1, 1, 1 as we go up, the most overlap between the x squared minus y squared orbital, then the next most by the xy orbital, a little bit of overlap with the dz squared orbital. We want to remember this pattern when we have a square planar geometry. This is how our d orbitals look in that energy landscape. Once again, octahedral, we had a few different situations. For square planar geometries, well, all of our complexes will be low spin. We will always pair up down low before moving up to these higher energy orbitals. Additionally, we're almost always going to have a d8 electron configuration. And so when we're filling in our electrons, it's almost always going to look like this. 4, 5, 6, 7, 8. We're going to have one empty orbital on top for that d8 electron configuration because it's almost always going to be low spin. All right, we have one last question to wrap things up. Will these compounds be paramagnetic or diamagnetic? Can we draw the electron diagram? Can we figure out the geometry? Can we figure out if they're high spin or low spin based on all of our knowledge from this chapter? We can look at this first one together. We have RHCN6 3-. We have rhodium with 6 cyanoligands. We will call this hexacyanorodenate 3. Well, okay, there's the name. Now let's figure out what we have going on. The geometry here will be octahedral. We have 6 ligands. We have to have this octahedral geometry. Our energy diagram for octahedral complexes, we have 2 orbitals up high. We have 3 orbitals down low. And this energy gap is our delta. We can look at our ligand to decide how big that delta is. We have cyanoligands, which means our delta is going to be large. We expect our complex to be low spin. We expect our complex to be strong field. Next, we can consider our rhodium 3+. Rhodium 3+ has what electron configuration? If we have 4d6 as our d electron configuration, we want to fill in our d electrons, 1, 2, 3. For a strong field ligand, we're going to have low spin, 4, 5, 6, all filling up down low. This compound we can predict to be paramagnetic. All right, there are 2 more practice problems here. Again, the strategy. Can we figure out the geometry? Can we figure out the electron configuration for our metal? If we have octahedral geometries, we need to go a step further. Check out the ligand. Do we expect it to be strong field or weak field? For tetrahedral compounds, well, always weak field. For square planar compounds, always strong field. Then we can fill in our electrons and try to predict our properties. All right, I hope this has been helpful. If you have any questions, feel free to reach out. Thanks for hanging in there, and I hope to see you in our next video. Thank you so much, and have a great day.